You know, in chemistry, we spend a lot of time asking what happens when we mix things. But there is another question that's just as important, maybe even more important in the real world. How fast does it happen? That's the whole field of chemical kinetics, and we're going to dive right in. So let's start with a little puzzle. Believe it or not, the laws of thermodynamics tell us that every single diamond on Earth is unstable. It's actually trying to turn into graphite, the stuff in pencils. So the big question is, why isn't your diamond ring slowly turning into a pile of gray dust? The answer has nothing to do with if it will happen, but everything to do with how fast. And that right there is the key difference we're talking about today. Thermodynamics tells you if a reaction is even possible, right? Is the destination downhill energetically? But it's kinetics that tells you how long that trip is going to take. It's the reason a diamond can last for millions of years, even though it's technically on a one-way road to becoming graphite. All right, so here's our game plan. We're going to build this whole picture from the ground up. We'll start with just how to measure reaction speed, then we'll uncover the formula that actually predicts it. Then we'll get into the fun stuff, using a little calculus to track a reaction's progress. And finally, we'll look at the two big ways we can control speed: temperature and catalysts. Okay, first things first. How do we even talk about the speed of a reaction? I mean, before we can start controlling things, we have to have a way to measure them, right? So, what is a reaction rate? Well, it's actually pretty simple. It's just how much the concentration of a chemical changes over a certain amount of time. Seriously, think of it just like a car's speed. But instead of kilometers per hour, we're talking about something like moles per liter per second. And we can see this perfectly on a graph. See how the concentration of our starting material, our reactant, goes down as time moves forward? Now, if we want to know the average speed of the reaction between 2 points in time, all we have to do is draw a line connecting them and find the slope. That gives us a pretty good idea of how fast things were moving during that period. But an average isn't always what we need. What if you need to know the speed at one specific single moment? For that, we need the instantaneous rate. And the way we find it is pretty cool. It's calculus in action. You draw a line that just barely kisses the curve at that single point. That's called a tangent. And you find the slope of that line. That slope is the true speed of the reaction, right at that very instant.
So we can measure the rate. That's step one. But the next, much more interesting question is what actually controls that rate? And that's where we get to the rate law formula.
The rate law is basically the master equation of kinetics. It's a beautiful little formula that ties the reaction's speed directly to how much of each reactant you have. That K is called the rate constant. It's a unique number for every single reaction. But the real secret sauce is in those exponents x and y. They tell us exactly how much the speed changes when we change the concentration of each ingredient. Now, here is the single most important rule about the rate law, and you got to remember this: you cannot guess it. You can't just look at the balanced equation for the reaction and figure out those exponents. Nope, they have to be found by doing experiments. At its heart, kinetics is a science of measurement. So, how does that work in the lab? Well, take a look at this data here. A scientist ran the same reaction 4 times. Each time, they just changed the starting amounts of the reactants, NO and O2, and then they measured how fast the reaction began. Our job now is to be a detective and find the pattern in this table. Okay, let's put on our detective hats. First, let's compare experiment 1 and experiment 2. Notice how the oxygen level is the same, but the nitrogen monoxide has been doubled. Now look at the rate. It jumped from 0.096 all the way to 0.384. That's 4 times faster. So we double the reactant, and the rate quadruples. That means the rate must depend on the concentration of NO squared. Got it? Okay, now let's compare experiments 1 and 3. This time, NO stays the same, and we double the O2. What happens to the rate? It goes from 0.096 to 0.192. It just doubled. So we double the reactant, and the rate doubles. That means the rate depends on O2 to the power of 1. And just like that, we've figured it out. We found our rate law, proven by experiment. This is a perfect moment to clear something up that trips a lot of people up. The order of a reaction, that's what we just found. It's the sum of those exponents we discovered in the experiment. But molecularity is totally different. That's a theoretical idea about how many molecules are actually bumping into each other in a single tiny step of the reaction. So one is measured in the lab, the other is a theory. They're not the same thing. Okay, time to level up. The rate law is great. It tells us the speed right now. at a specific concentration. But what if we want to predict the future? What if we want to know the concentration at any point in time? For that, we need to build a more powerful tool using some calculus. It's called an integrated rate law. Let's see how we derive it. Now don't worry, we're going to walk through this together. Step 1, we start with our basic rate law, which is all about an instantaneous moment. Step 2, we do a little algebra to get all the concentration stuff on one side and the time stuff on the other. We're just getting it ready for the next step. Step 3, we integrate. Integration is just a fancy calculus tool for summing up all those infinite, tiny moments over a period of time. This gives us a new equation, but it has this mystery constant I. So for step 4, we solve the mystery. We just plug in something we know is true. At time 0, the concentration is whatever we started with. And bam, that gives us our final, powerful equation that connects concentration directly to time. So why on earth did we go through all that math? Because of this. Check it out. The equation we just built is secretly the exact same formula for a straight line. You know, y equals mx plus c. This is huge. It gives us an amazing way to test our theories. If you think a reaction is first order, all you have to do is plot the natural log of its concentration against time. If you get a perfect straight line, you were right. The math we just did predicts the shape of the graph. That's so cool. One of the most practical uses for all this math is the idea of a half-life. The question it answers is really simple. How much time does it take for exactly half of my starting material to be used up? And here's where it gets really interesting. For first-order reactions, like radioactive decay, the half-life is always the same. It is constant. It doesn't matter if you start with a mountain of stuff or just a handful of atoms, the time it takes for half of it to disappear is always the same. This is the science behind carbon dating, and it all comes back to that one rate constant, K. So far, we've seen how concentration is a huge factor in controlling reaction speed. Now let's talk about the other big one, something we all know makes a difference: temperature. You see, for a reaction to actually happen, it's not enough for molecules to just gently bump into each other. They have to collide with some serious energy. That minimum amount of energy needed to get the reaction started is called the activation energy. Think of it like a big energy hill that the reactants have to climb over before they can become products. This diagram shows that energy hill perfectly. The reactants are just sitting there in a low energy valley. To turn into products, they need a big boost of energy to get to the very top of that hump, to a place called the activated complex. The height of that hump is the activation energy. The higher that hill is, the fewer molecules are going to have enough energy to make it over, and the slower the reaction is going to be. So if the height of that energy hill is what's controlling the speed, is there any way to, make the hill smaller? Oh yeah, there absolutely is. And that's the job of a catalyst. A catalyst is one of the coolest things in chemistry. It jumps into the reaction and makes it go way faster, but it comes out totally unchanged at the end. So how does it do it? Well, it creates a brand new pathway for the reaction to take, a shortcut that has a much, much lower activation energy. A catalyst doesn't give the molecules more energy to climb the mountain, it builds them a tunnel to go straight through it. And there you have it, our deep dive into chemical kinetics. By understanding rate laws, activation energy, and catalysts, we go from just watching chemistry happen to actually being in control. We can speed up the creation of life-saving drugs or slow down the spoiling of food. We get to set the tempo for the chemical world all around us.